Hi everyone, I'm Jean-Sébastien Brouillon, and thank you for watching this presentation on robust online joint state input and parameter estimation of linear systems. Now, there's many keywords in this title. Robust means that you want to deal with different kind of noise. Online means it has to be executed in real time. And joint means that you want to simultaneously estimate the state, the input, and the parameters of the system. The main motivation is that we face increasingly complex systems that are very large scale, like a smart grid or a smart city, where it's often impossible to fully model the dynamics. On the other hand, we can leverage the progress in sensor technologies that has been made in the recent years, and that gave us many very cheap sensors that we can put everywhere. So we have an overabundance of data, but the quality of this data is fairly low. The last argument is for sustainability. Tracking the variations in the parameters of the system may allow you to extend its life. The traditional paradigm in system identification is to have a large system with very few inputs, but many unobservable states inside that you need to infer from the few inputs. And this is in direct contrast with this new models of very large scale system with lots of sensors spread everywhere, and where you measure almost all of the states, and often you even have several sensors per state, which is called sensor fusion. But all these sensors have different statistical models, and the noise is often not very standard. So you need to take that into account. Now, traditionally, we have a very strong assumption on the noise, and we don't really care too much about this in the control systems community. We assume that the noise is Gaussian sentence is very common in paper. Who has ever put it in his? I'm the first one. But it's not always true. For example, if you have a visual motion tracking system, I plotted the distribution of the error here on the position estimate of this soccer ball. And you can see that there's a lot of noise in the tails. There's some outliers. And if you try to fit a Gaussian distribution, you won't be too successful. So there's many methods for this, but one very effective one in the field of statistics and machine learning is to use tail-heavy distributions. A very common one is the Laplace one. When you have matrix-valued parameters, it can translate in different problems. Usually the log of the Laplace is a simple L1 norm, so a sum of absolute values. If you have matrices, it can be a nuclear norm or just the sum of the absolute values of all the entries. There are several solutions there. The second fix is regularization, which means that you add a penalty on the magnitude of the parameter estimate in order to introduce a bias, but reduce the variance of the estimates. And this has picked up a lot of interest recently because of its equivalent with robustification or even distributional robustification. Now, to maximize the robustness, you'd want to do both. How do you do that? If you have a system with this very well-known dynamics equations, if you want to do joint estimation, you have to maximize the likelihood of the estimates of parameters, states, and input, which means minimize this L1 norm on the difference between what you predict using the system model and what you actually measure as a state at xt plus 1. So if A and B are in red are the parameters of the system, in blue you have the state trajectories, and in green the input trajectories. When you use these two, you can predict the state trajectory at time t plus 1. And if you have zero noise, it would be perfect, but you try to predict it as best as possible, so you try to minimize the difference between them. Now, we know that there are a lot of identifiability issues with this problem because you don't know A, you don't know B, you don't know the exact state trajectories, and you don't know the exact input trajectories. So you have way too many unknowns and just one equation. So one solution is to, if you have the state trajectories, even noisy, symbolized here by the trajectory with some little vertical bars, which symbolize a confidence interval, you can say that you want to fit the data as good as possible because you assume the noise to be Laplace distributed. So you add an L1 penalty on the difference between the state trajectories that you measure and the ones that you estimate. Always want to fit the data. If your input is also noisy, you can do the same. And finally, you can add parameter regularization to benefit from the second robustification method. And that means that you add a penalty on the difference between your parameter estimate and some prior value that you knew before. Usually people just use 0. That's equivalent to the lasso penalty or the ridge regression penalty. And it provides you with good enough results if you have no idea of what A and B should be. Now, this 3 terms problems is very hard because it's non-convex, so you can only hope for a local optimum, even though if your data is quite close to the real state and input, you are in the neighborhood of the global optimizer. So you usually end up there at the end of the day. The second problem is that it's non-smooth due to the L1 norm, so first-order methods are challenging. It's also bilinear because the states multiply the parameters. And finally, you want to execute this online. So you have a very hard optimization problem that you want to execute very fast, possibly in embedded situations. So it's very challenging. Now, there are 3 solutions to those last 3 problems that exist in the optimization community. The first one is iterative reweighing. It's really known for iteratively reweighted least squares. And essentially, it amounts to saying that the absolute value of a random variable x is equal to x squared divided by the absolute value of x, which amounts to taking an L1 norm being equal to an L2 norm squared weighted by the inverse of whatever is inside the norm. Now, this is doable as long as you don't have 0 values. If you have 0 values, you divide by 0, so it's a bit complicated. So you can just add a numerical stability constant on the denominator called alpha here. And this transforms your problem from a non-smooth linear problem to, bilinear problem to a quadratic bilinear problem. And that's usually easier to solve. It's very common to do this for iteratively reweighted least squares. Now, the second problem is the bilinearity. Ideally, you'd want to have a linear problem that has a closed form solution. It's much easier. So one solution for this, known in optimization, is alternated descent. So what is it? It consists in fixing the parameters to a starting value and estimating only the state and input, because then you obtain the following linear problem inside the L1 norms at least, or reweighted L2 norms. And you can update an updated state and input estimate. And now you can fix that and just solve with respect to the parameters A and B. So it gives you another linear problem. Note that the second term has disappeared because it doesn't depend on A and B, and the third term has appeared again because it did not depend on the state. So you have those 2 linear problems with much simpler to solve, which are much simpler to solve. And you can alternate between the 2 until it converges. Now, the last problem is the online execution. If you just implement this as it is and try to solve it over time, the state trajectories will grow because you get more and more samples and you therefore have more and more things to estimate. And this enlarges your optimization problem at each step, which makes it very challenging to solve. Now, one common solution is just to use the correlation matrix, which is the inner product between the trajectories. And this is a square matrix with a fixed size, so no exploding. But it still obeys the state dynamics, which means that the top part of the matrix is equivalent to the state at t+1, and the bottom part of the matrix contains kind of the input and state at time t. So you still have the state dynamic equation that applies. And this is very common in recursive least squares or the Frisch scheme. There's a lot of different methods that use this technique. Now, what is new? The novelty is in combining all 3 techniques because they've been used on their own for different problems, but never really together. And the naive way to do this is you take this correlation matrix, you update it like any other method would do with a forgetting factor maybe, and you add the new samples. And then you use the iteratively reweighted loop for the first part of the alternated method. So you try to solve what is the best estimate for C, given some parameters A hat and B hat. And since this is iteratively reweighted least squares, you end up with a solution which is just a projection of C on the null space of this matrix minus I A hat B hat, weighted by the previous residuals. So this is just a simple loop. You wait until it converges, and then you can go on to the A and B problem. So now you fix C to what you found before, and you do again the iteratively reweighted least squares, which gives you this closed form solution with an oblique pseudo inverse. And you can, so it's weighted by again by the previous residuals, and you can loop over that, execute it until it converges, then you get your estimate for N, B, and you rinse and repeat for C. But now you have a double nested loop that you have to execute at each time step. And this is very slow. It's not possible to do online. So what if you just try to do one part of the loop, let's say the A and B, and you fix C? Well, that's equivalent to saying that the system is at steady state, because if the new samples are the same as the previous ones, at t equal infinity, the C matrix doesn't change. And you can actually observe that the algorithm converges at steady state. And I'll give an outline of the proof later. But first, this is still too slow. You still have a loop at each time step. So what if you just want to do one iteration of this loop and call it a day, or like 2 or 3 if you have time, but minimum 1. So will this converge? It turns out that it does, under the condition that your noise is bounded and your C matrix is rich enough. And this C matrix, the largeness, the richness of the C matrix is directly linked to the forgetting factor beta, and I'll explain you why later. But you can see that there's always a beta such that your C matrix satisfies the second condition, and then the theorem, the convergence applies. So first, at steady state, why does it converge? You have every time least square solutions, which means that the residuals written here by minus I A hat B hat times C hat, their 2 norm decreases because the projection matrix has only 0 and 1 eigenvalues, so it cannot increase the value of this norm. This gives you a Lyapunov argument because the 2 norm is lower bounded by 0. Now, when you're not at steady state, you have to be careful because the C matrix may increase that norm, which cancels the Lyapunov argument. And to avoid this to happen, you need the new sample not to make that C matrix grow once you're at t equal infinity. And this can be done by setting a high enough beta such that the value of the C matrix is very large compared to that new sample. And this gives you the following inequality where your forgetting factor, 1 minus beta, needs to be smaller than some function of the bound of the noise and the richness of the correlation matrix. Well, this works in theory, but does it in practice? We applied it to a small system, 2 by 2. And first we tried standard methods like subspace identification and the extended Kalman filter, where the state is augmented with the parameters. So it gives a bilinear system. And it's a very common method for joint estimation problems. And you can see that with even 1% of outliers, on the left, you have the mean square error of the parameter estimate after 50,000 time steps. And you can see that it has 50% error with only 1% outliers. So it's not very good. Now, this error is due to both the joint estimation and the outliers. The recursive total least squares is better suited for joint estimation, but assumes Gaussian noise and has a significantly lower error. But our method, the AIRLS, achieves much lower error with about 1% for 1% outlier. So you can see that you can really benefit from doing this one-step update. And what this reduced error on the means on the trajectories, the smoothing of the trajectories. On the right, you can see that EKF and subspace identification always smoothes the state way too much. It's very close to zero. And if you have a better estimate, you will be able to fit the spikes a lot better. I also applied this method to different applications, which are not in the scope of this paper, but I did parameter identification for power grids, because very often you have bad signal to noise ratio, so you need to do joint identification. And I managed to get really good results for this problem. So there are other applications where you can use this estimation method. Another question left open in this paper is, does it actually converge to the real parameters and states? Or because I proved I converge to a fixed point, but is that fixed point what you're looking for? And in a later time, I proved that it's actually the case if you're alpha, so the numerical stability parameter, so that you don't divide by zero in the iterative reweighing, remember? If it's not too big, then you'll end up in a neighborhood of the solution. And the size of that neighborhood depends on how big alpha is. Finally, can you solve harder problems? Now we have a bilinear problem with states multiplying parameters. Can you do trilinear, quadrilinear, anything? And I formalized this as a maximum likelihood estimation of random variables in a Bayesian network, because Bayesian networks, if the variables are continuous, they provide a graphical model for basically any statistical problem. And what you can use this method for is if your probabilities follow this equation, that means that it's a probability of a multi-affine function of the random variables. Not going to get into details here, but if you have this form, then you can use that method to converge to the maximum likelihood estimator. So it can solve much more complex systems, problems. So. Now, as a summary, we've seen that system identification is a change of paradigm, more towards machine learning and statistics, because you have more and more sensors, more and more data, and the statistical models aren't always so trivial. And that results in a very hard problem to solve that I combined 3 different optimization methods to solve. But this is very hard to do in real time. So finally, I proved that if you just do one step of each of these iterative methods, you still converge to a fixed point, which is close to your solution. Thank you for watching, and let me know if you have any questions.